Hello and welcome to the solutions video for both versions of our Unit 3 unit exam. So we will start the one for Jubin, simply because these are alphabetized by last name. Alright. So, a light ray has an incident angle of 63 degrees on mirror A. The mirror is placed so that it and a second mirror B form an angle of 97 degrees. We need to find the angle of reflection from mirror B. Well, this will be easier if we draw a picture. So we have one mirror here, another one at a 97 degree angle. And our light ray comes in at about a 63 degree angle. It'll reflect. This is not even remotely to scale, but we'll make it work. So if it comes in with an angle of incidence of 63 degrees, always measured relative to the surface normal, that means this angle is 27 degrees. So is this one, because that's how reflection works. We get exactly the same angle. So now 27 and 97, those add up to 124. All three angles in this triangle have to add up to 180. So we need a 56 degree angle here. And now that and our angle of reflection add up to 90. So this is a 34 degree angle by the time it's done reflecting. So we put in the 34. Here we go. Light of wavelength 197 nanometers hits a metal with a work function of 2.70 electron volts. So what's the kinetic energy of the electrons ejected from the metal in electron volts? So the energy of the photon is going to be the kinetic energy of the electrons and the work function. It's going to be divided into these two energies. So the kinetic energy of our electrons is the energy of the photon minus the work function. So that is hc over lambda, since they gave it to us as a wavelength. Now our h, most conveniently, use the version that is in electron volts, or electron volt seconds. 3.00 times 10 to the 8 meters per second, all over our wavelength of 197 nanometers. So 197 times 10 to the negative 9 meters. And from that we subtract our work function, which I think was 2.70 eV. It was. So, I don't have a physical calculator with me. So we will come over here and hit our emulator. We'll go full screen, OK to enter calculation mode. Now, 4.14, let's make sure we've got the right one. Yeah, 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 197 times 10 to the negative 9. So that's the energy of the photon in electron volts. So we have to manually type answer minus 2.70. That's subtracting our work function. And here we go, 3.60. They want it in scientific notation, so it's 3600. Right. If we wanted to increase the photoelectron current, how would you modify the incoming light? You'd increase the intensity. We're not looking to increase voltage. We're not looking to increase the stopping voltage. We just want more electrons moving. And since we need one photon to come in for each electron that we get, we have to increase the photons coming in. And that's increasing the intensity. Now, if we want to increase the kinetic energy of the photoelectrons themselves, here we'd have to increase the energy of the photon itself. So we either have a higher frequency or a lower wavelength. These are the options that we have in front of us here. All right. So next, students place the light from a cell phone at the 0 centimeter mark on a ruler and a converging lens of a hand magnifier at the 5 centimeter mark. So we have our focal length. We want to know where we put a sheet of paper to see a focused image. So that means we have a 5 centimeter object distance and a 2.98 centimeter focal length. So, our 1 over f is 1 over dO plus 1 over di. I apologize in advance if I misremember any of the formulas. I didn't bring the formula sheet home with me, so I'm working purely by memory here. So the reciprocal of di would be 1 over f minus 1 over dO. So that's 1 over 2.98 centimeters minus 1 over 5.00 centimeters. So again, with this calculator, 1 over 2.98 minus 1 over 5.00. And then we will reciprocate that answer. Does this have a simple reciprocal button? I think I'm going to have to go answer to the -1. I think this is one of the few calculators that actually takes the minus as the negative. So that is giving us, to 3 sig digs, 7.38 centimeters. Multiple choice. Polarized sunglasses can be used to reduce glare. Well, light is reflected from the road and is polarized in a horizontal direction. Well, not necessarily. Sunglasses help whether there's roads in sight or not. Light from the sun has a unique spectrum that can be filtered out. Well, it's true that it has a unique spectrum, but we don't filter that with polarized lenses. So, they filter out light from artificial sources, which are always polarized. They are not always polarized when they're artificial. Glare is present only in the fringes, while you see the central spot. So, B, C, and D are flat out false. So A is true. They reduce glare for other reasons, but of these multiple choice reasons, that is the best option. Really, light from the sun is polarized in a variety of directions. So if you break it down as either vertical or horizontal, and you can break down every photon as some combination of vertical and horizontal because they're random, perfect polarization will cut out half the light. Number 2. A group of students wants to demonstrate the total internal reflection of laser light using a transparent dish containing water whose index of refraction for this wavelength of light is 1.33. To achieve total internal reflection, the light must start in one of the materials and must form an incident angle of blank with the dish's normal. So for total internal reflection, you have to be going from the higher index of refraction to the lower. So you have to be going from water into air. Now, if you have 0 degrees, you never have refraction of any kind. It'll always pass straight through. So it can't just be 49 or less. It's got to be above the critical angle. We could solve for that critical angle. We don't have to with this problem. It's basically telling us it's 49 degrees. But with Snell's law, we're looking for n2 over n1 equals sine theta 1 or sine theta 2, where the one we know, so in this case theta 2, is 90 degrees. So this will hit just the surface of the water instead of coming out. So that makes material 2 our water, material 1 air. So then the sine of our critical angle is 1.33, because this is 1.33 divided by 1. Sine theta 2 is 1. So theta 1 is the inverse sine. Oh, sorry, 2 is air. This has to be 1 over, or we're not going to get the inverse sine. So if we take the inverse sine of the A sine of 1 over 1.33, we get our answer in radians. I forgot that's the default mode on this calculator. We'll just manually convert. And there we go. There's the 49 degrees that we're seeing in the multiple choice. So just in case that critical angle comes up in numeric response or in written response, that's how we find it. Number 3. Students use a green laser pointer and a grating to produce an interference pattern on a ruler as shown below. So the ruler is 30 centimeters from the grating, and the wavelength of the green laser light is 557 nanometers, pointed at the 0 centimeter mark on the ruler. The best estimate of the distance between slits as determined by the student's measurement is, and if they replace green with a red laser, the bright spots will move in which way? So if you replace a high energy with a low energy, then you're going to get more diffraction. The more energy, more momentum we have, the more likely it is to come straight through. So part 2 has to be away from the 0. So that means we're either looking at A or D. Now, for the diffraction equation, sorry, it's hard to type with a stylus in my hands. Just, as I said, I left the formula sheet at home, so let's see if we could find the exact. So there's the formula. So sine theta is lambda over d, or here, sine theta n is n lambda over d. So there we go. Sine theta n is n lambda over d. So n is the fringe number, lambda is the wavelength, d is the distance between slits. So then d would be lambda over sine theta 1 if we use our first fringe. Now our wavelength is 557 nanometers. We don't have the sine of this angle, but we can use our approximation, where the approximation for that angle is the distance the light diffracts, in this case about 4.1 centimeters, divided by the distance from the screen, which is about 30 centimeters. Note we have that ratio, centimeters over centimeters, is going to cancel. So if we just do the 557 times 30 divided by 4.1, our answer will be in nanometers. So 557 times 30 divided by 4.1 gives us about 4,000. And that's if the small angle approximation holds. This is actually too big for the small angle approximation. So we'll use the inverse tan. So I'll use the inverse tan on my phone's calculator. Right, but what we had was, excuse me. Remember, this came out in nanometers, so our 4 converts. It's a little bit off, but that's because of our ability to measure these angles when it's on screen. Now this one is a little bit tougher. We need the focal length of the mirror as measured by students. They have 1 over di versus 1 over do. So these are x and y. So our slope of this line. We want to find the slope, and we want to find the frequency, or our focal length. So how have they linearized it? Well, if y is 1 over di, that means we have 1 over di, that's going to equal a negative 1 over do plus 1 over f. So the reciprocal of our focal length is going to be on our y-axis. And that looks like it's coming in about 0.075. Just roughly speaking. So if we have 1 divided by 0.075, we get about 13.3. So we want to do it a little more precisely here with this. And I'm actually seeing 13.8 is the number in the answer key. We do a little bit better if this was physical paper where we could pull out a ruler or even use that ruler to do more accurate measurements of the individual points and put it through a regression algorithm. All right, our last two. You stand in front of a concave mirror whose focal length is 44.1 centimeters, looking at a 0.457 centimeter long hair in your eyebrows. Your hair is 43 centimeters from the mirror. So, how big will the image of the hair be? Okay. So, let's find our magnification equation. HI over HO is a negative DI over DO. Okay, so HI over HO is negative DI over DO. All right, so we want to find the height of the image. So HI is a negative DI over DO times HO. The distance to the image. Okay, we have the focal length and we have the object image. We have to get the distance to the image from that. Okay, so we can't do this step quite yet. we have to do 1 over f is 1 over dO plus 1 over di. So di is 1 over f minus 1 over dO. And that is what we substitute into here. So our di 1 over, and inside it's 1 over, and our length is 44.1, I think, our focal length. And the other one is 43. Okay, so our image is not particularly close. And we take this and divide it by the negative of our object distance times the height of the original object, which is 0.457. And this gets us to 18.3. So, notice the image is positive. So, yeah, the distance to the image here, 1 over f minus 1 over dO, that came out negative. And we are dealing with a concave mirror. So this negative distance means our image is behind the mirror, which makes it virtual. And our height of the image came out as a positive number, so it is upright. So I'm just checking here. There's half a mark for numeric response 3. Right, 7.38 here. Okay, that one, I didn't read the question carefully enough. 7.38 is the image distance. That's how far behind the mirror it is. But this is asking where we put a sheet of paper on the ruler. So we have to add those 5 centimeters to it. So that has to be 12.4 to count for the exact position on that ruler. So that is the solution set for Jubin's test. And now we will do the solution set for Harmangeat's. Okay. So, first question. In order for light to be totally internally reflected within the glass, or within the glass with n equals 1.58, the light must, well, we know we have to travel from air to the glass. It has to be dense. We have to be greater than the critical angle. We've already seen how to solve for that critical angle on Jubin's test. So now here, it's a similar setup, but we notice we have different numbers. But again, the same idea of finding that focal length. We do a linear regression, we find that vertical line, and we reciprocate. So in this case, it's going to be 27.8. So you use a magnifying glass of focal length 15.3 centimeters to view a bug with a size of 1.45 millimeters. If the bug is 18.5 centimeters from the lens, its apparent size when viewed through the magnifying glass will be. So this is identical algebra to this problem here that we had at the end of Jubin's test. We just have different numbers. So I will leave it to you to try that on your own to make sure you understand how to get those numbers. But it comes out to that 6.93 millimeters. Now, monochromatic 550 nanometer light is incident on a pair of slits that are this far apart, producing a first-order bright fringe this far from the central maximum. The distance from the slits to the screen is... So this is coming back to this equation, using again our x over L approximation for sine theta. So we've got that x over L. So let's actually see if we could find the exact value. Was that in here as well? Okay. Let me find the equation. All right, let's just continue. So we had sine theta n is n lambda over d, and we're going to approximate sine theta as x over L. That means dx over L lambda is approximately n. So we have a first order bright fringe. It's this far from the central maximum. The distance from the slits to the screen. So we are looking for L. So L is going to be dx over n lambda. D is the distance between the slits, 4.35 times 10 to the negative 4 meters apart. X, how far we are from that central fringe. That's 2.78 times 10 to the negative 2 centimeters. 10 to the negative 4 meters. It's the bright fringe away from the central, and then here, 550 nanometers. So 550 times 10 to the negative 9 meters. So that's what we have, 4.35 times 10 to the negative 4. And we are multiplying that by 2.7 times 10 to the negative 4. We're dividing that by our 550 times 10 to the negative 9. Times 1. So this gives us a 0.2135. That is our length. So yes, 2 is B. With some minor round-off error, it's the only one that's close. I'll track down the generation of the question to resolve the round-off error. An object is viewed in a convex mirror with a focal length of 10 centimeters. If the object is 2 centimeters tall and 5 centimeters from the mirror. Do we have our lenses available here? No, because we didn't save. So, we need to find at least the distance to the image. That will help us narrow these down. So 1 over f is 1 over do plus 1 over di. So the distance to the image is 1 over f minus 1 over do. So our focal length is 10 centimeters. Our object is 15 centimeters from the mirror. So 1 over 10 minus 1 over 15. So there we go. Our image is 30 centimeters away. So we have to figure out, is it going to be enlarged and real or diminished and real? So clearly it's going to be real. We have to figure out, is it enlarged or diminished? Well, our object distance and the image distance come back to our magnification. So the image is 30 centimeters away. That's double the distance to the object. So the height of the image has to be double the height of the object. So it's going to be enlarged. And that's not what this is saying. Sorry, the answer key is key to A. Diminished virtual and 6 centimeters from the mirror. Okay, let me see if I messed up a sign somewhere. Allow me to pause the recording while I look into this. Okay, so let's continue our investigation together. Now that I've got our mirror, I'm going to save it this time so we can always find it with the student. But now our mirror, we are looking at focal length of 10, which means our center of curvature needs to be 20. Now our object, the height of our object is 2 centimeters. And the distance to the object is 15 centimeters away. Yes, so the image is 6 centimeters away and it is diminished. So it's not an issue with the answer key. It is an issue somewhere in my algebra. I think that's purely because the real and virtual definitions with mirrors and lenses are reversed. So there should be a sign difference here. So we'd be adding them instead of subtracting them. If that's the case, would that have done the trick? That would have done the trick. All right, so that was the sign difference in the definitions with that convex mirror rather than a convex lens. Okay. So now, an electron at rest is bombarded with a photon of frequency 8.37 times 10 to the 22 hertz. After the collision, the photon scatters at an angle of 12.5 degrees. We want to find the frequency of the photon after the collision. So this is Compton scattering. So we need our equation for Compton scattering. Here we go. So the change in wavelength is h over mec times 1 minus cos theta. So delta lambda is h over mec times 1 minus cos theta. We've got our theta, and we have our initial energy. So delta lambda, our h here, do we have a preference in units? Doesn't look like it, so we'll use the SI unit, 6.37 times 10 to the negative 34 joule seconds, all over 9.11 times 10 to the negative 31 kilograms. 3.00 times 10 to the 8 meters per second. 1 minus the cosine of 12.5. So 6.63 times 10 to the negative 34 joule seconds divided by 9.11 times 10 to the negative 31 times 3.00 times 10 to the 10 to the 8 times, and then in brackets, 1 minus the cosine, and I realize now we're in radians, so 12.5 degrees times pi over 180, because I forgot to change this calculator's mode. So we have a 5.75 times 10 to the negative 14 change in wavelength. 5.75 times 10 to the negative 14 meters. So this wavelength, though, is C over our final, minus C over our initial frequency. So the final frequency we are asked for we'd reciprocate this whole thing and then multiplied by C. So we have a C in the denominator here. We don't have one there. Okay, so this is going to be 3.00 times 10 to the 8 times, we open the brackets, and inside the brackets we have 1 over our answer plus 3.00 times 10 to the 8 over our initial frequency of 8.37 times 10 to the 22. So this gives us 4.91 times 10 to the 21. Anytime we're dealing with collisions, we're going to be dealing with conservation of momentum and conservation of energy. And how do we use the laws of physics to explain this? Well, light has momentum. That's the property. That's what we're doing with any collision. All right, eclipses of the moon of Jupiter are observed from 2 locations, A and B, that are about 6 months apart. At point B, eclipses are observed 22 minutes later than they would have been expected based on observations at point A. So we have the orbital diameter of the Earth. So the difference between these 2 points, which are roughly 1 diameter apart, takes 22 minutes for light to travel that far. So if we take our 3.00 times 10 to the 11 meters and divide it by the time involved in seconds, so that's 22 minutes times 60 seconds per minute, we end up with about 2.27 times 10 to the 4. Or about times 10 to the 8, not times 10 to the 4. Now here, mirrors A and B are perpendicular. So we have the angle here. We want to find the distance from B at which the reflected ray strikes mirror BC. So we have a right triangle where the tangent of 38, because that's the interior angle on the right, is equal to the opposite divided by 4. So, might be a little late, but let me actually change this. Settings, angle measure. Let's go degrees. All right, now we're in degree mode. So 4 times the tan of 38 gives us about 3.13 centimeters. Finally, which of these has the lowest frequency, that has the lowest energy? That is the microwave on this list. So now quickly checking our written response. And that was actually silly. In the first one, it has to go from more dense to less dense. So from glass to air, not from air to glass. Going too quickly after switching it because it was a similar problem. But that is the set of solutions for both versions of the test.